Okay, great. So thank you. So my interest is sort of strongly nonlinear materials. And when we started to describe or started to think about describing these systems, we sort of discovered that a perspective of information is useful. And the reason I'm here is that we're also starting to think of, can we actually use this for information processing? So this is one of my favorite complex systems, a crumpled sheet. And the idea is, if you want to describe these systems in many ways, it's completely hopeless. But maybe what you can do is really think of the sort of multi-stable things that pop in this sheet, and maybe you can describe them with bits, and then when you drive the system, the bits change, and you can think of this as information processing. Now, this is, of course, a schematic picture. What I'll do is show you very quickly a few examples of what we've been doing with physical systems. We have a single input, and then I want to talk about also what you can do when you have multiple inputs, because I think that enlarges really the amount of compute that you can do. So, as a first example, it's a very simple system. It's a plastic sheet which has grooves in it, and each of these grooves you can think of as a material bit. So currently all the bits are in state 0, but if I pull on this system, all the bits go to 1. So something pops, there's really a clear distinguishable 0 or 1, and that changes the shape of your sheet. So it's not really a computation, but you can think of it maybe as a computation in the sense that you provide an input and then the outcome of your computation is a shape. And by giving it different inputs, you can actually get a lot of different shapes, and this is simply the same sheet. So you can sort of write bits in it, gives you a shape, you can erase it, you can write other bits. Okay, that's maybe not a very traditional computation. So then we started thinking, can we do something which you would recognize? So we thought, can you make a material with material bits that can count? And in this case, we have a mechanical metamaterial. It's something you can hold in your hand. All of these beams can buckle to the left or the right, which is encoding a 0 or 1. And if you repeatedly increase, if you repeatedly compress this system, you see that it counts. So every time you do this, there's one state that's being copied here. So the system has sort of a memory of how often you compress it. So it's a very simple computation. And the idea is, again, that we have multi-stability, multi-stable elements, and we couple them. Okay, and that allows you to do things that look like information processing. Maybe an example that's sort of in between. So this is one of these corrugated sheets, but it's a much smaller one, so it only has 3 bits in it. And if you look carefully, if I now repeatedly compress it, it can count to 2, which again is not very impressive maybe in terms of computation, but it's a start. So the first time you compress it, and the second time you compress it, you end up somewhere else. Now these were the first things that we're starting to do, but then we started to think, I mean, this is not designed, so I really don't control the computation here. This is designed, but was very complicated. And so maybe a simpler principle is when you, is like this, where you actually make a network of these bistable elements. And this gets a little bit closer to computation. So here I have 3 bistable elements, and by putting them in a network, I control the interactions. And so in this case, we could actually control when each of these bits is switching, but also how one of the bits is influencing the other bits. And that allows you to do computations as follows. So I'm going to pull and push on the system here, and I'm going to follow how these bits evolve. And what I'm going to do in this particular example is the amount of driving that I do. I will do negative and positive peaks, and I'll think of these as 2 different characters of an alphabet of inputs. And actually here you see precisely how it works. So I start out here and I either go back or I go up, and that's an A or a B input. And if I do this, I get a little finite state machine out. And it works as follows. I'll just show you the movie. If I start in this state and I do a B pulse, nothing happens, so that's very boring. If I'm now going to do an A pulse, I go to this state eventually, 110, so I have to go back, 110, there you go. And I hope you believe me that if you run through this thing, that all these transitions are there. And so it's a very frugal way of computing in some sense. You have 3 elements, you get this thing out, and actually, if you play with the type of inputs, the magnitudes of each of these pulses, it turns out that this single sample encodes 18 different finite state machines. And some of these, if you wanted to build this just with logic gates, you need a couple of flip-flops and some logic, right? So here we just use 3 elements. So maybe that gives you the idea that this is sort of a very frugal way of computing, and maybe to connect it to other fields. I don't know how to do this optically, but what I do know is that you could replace these elements by little nonlinear electronic devices, for instance, memristors, and then you could do these sort of computations also in an electronic way. So I think the general idea is to have these bistable elements, make them, connect them, so you get interactions and see what you can do with them. So that's when you have a single input. But of course, in many cases, and certainly when you want to do computing, you have multiple inputs. Why would you restrict yourself to a single input? And the point is now that often the order in which you then give input, of course, matters. This is, I think, very obvious from a computing perspective, but we were trying to think of how would that work in a mechanical context. And so this is the thing I want to talk about now. And we, again, didn't do it in a crumple because it's extremely hard, but we did it in a very simple mechanical system, which was sort of geared to be sequence dependent. So you can think of this as 2 pre-curved beams that are interacting. Here you see the beams. This is sort of a spring between the beams. And the idea is now I squeeze on them in a certain order and I see what happens. And here you see twice the same sample, and I'm going to squeeze at them in a different order. So first I squeeze here, and then I squeeze there, and of course you end up in a different state. You know, the thing was designed to be like that. If you want to think of this a little bit more physically, these elements are very close to a pitchfork bifurcation, but the symmetry is broken. So if you drive them without interactions, they know what they're doing. But if one of them already moves, then it basically flips the other one over, okay? So clearly you have something which you could call non-abelian. The sequence of input matters. Now, if you have one of these states, you can also ask yourselves what happens if I remove the driving. And also there the sequence matters. So that's a little bit more tricky, but I start from the same state, and now I remove the amount of compression in a different order. And in one case, the system will sort of snap, and in the other case, it will move smoothly. So you also have something which we call mixed mode dynamics. This is maybe a little bit too complex, but I'll show you how to think about this. So all of this has to do, as I said already, has to do with sort of the singularities that you have in your system. I'm not going to describe this in much detail, but people that are familiar with catastrophe theory may recognize this, and if you're not familiar, then I don't have enough time to explain it. But basically, in the space of driving, so epsilon 1 and epsilon 2, there's a singular point, and basically what is important in this case is how do you, in your driving space, which basically gives you the sequence of actuations, how do you navigate around that point? And of course, for more complex samples, you may have more singularities, and that adds to the complexity. So if you start here and you go there, you end up in one configuration. In this regime, we only have one state, but here we have 2 states. And if you go the other way around, you end up with another configuration. That's that sort of non-abelian response that I first showed you. And if you now lower the driving, it depends on if you're in this state, do we go here or do we go there? If I go here, the transition is smooth, but here the transition is non-smooth. That's the second phenomena that I showed you. And so you can build up this whole diagram. And it turns out for this simple system, you can really encode it in a diagram as follows. So these are my inputs. A 0 means no input, and a 1 means compression. And then I can simply follow what happens. So if I follow this path, I end up in one state. If I follow that path, I end up in another state. If my transitions are smooth, I represent them like this, and if they're non-smooth, so if there's a sudden switch. I will represent them with an orange arrow. Now what you can see here also is that probably the amount of driving that I do is important, right? So the amount of driving that I do here is, you know, initially I do not cross a border, but then I do cross a border. So you can play with that. And if you play with that, you can actually, out of this single sample, you can get different computations out. So basically the blue path gives you now the different amount of driving. If you start like this is a completely trivial circuit, so your input and output are the same. If you do like this is the one I just showed you. What I didn't show you is that this is precisely the same functionality as an RS latch, so it's a single bit of memory. If you drive it slightly differently, you shift the location of these transitions, and you get something like an RS latch with some additional logic there, and you can play with that. Now, the final thing I quickly want to show you is that we also have done this for slightly larger samples. So now you have 4 of these elements and a 4-dimensional input space. And it very quickly becomes very complicated. This is what the transition diagram looks like. This is actually something we determined experimentally. It's very hard to make out of this spaghetti what sort of computations you do. But one thing you can do is, for instance, take 2 inputs as sort of, let's say, as your programming of your device, and the 2 other inputs as inputs, and then you can program 4 different types of sequential logic. Or you could simply just go through all this thing and see what are all the simple motifs that you have when you only use 2 of the inputs. And all of these are sort of flip-flop-like with additional logic. And so what we conclude from this is that even this very simple system with 4 nonlinear elements that you couple have already a lot of hidden computation in this. Of course, we do it mechanically, but there is nothing preventing you to do this at another platform if you are sufficiently nonlinear. And to me, electronics is probably best suited for that. But we'll see. That's all I wanted to say. That's where I got the money from. These are the people, and these are some papers. Thank you.
So, yeah, Hecke.
So, the different functions you got by changing certain parameters, are you changing the amplitude?
In this case, it was only whether I squeeze or not. So there is another layer of complexity if I change the amplitude. So then I also will get multiple functions. I did 2 different things. For the 2-input system, I only played with the amplitude. For the 4-input system, I didn't show you that complexity. I only showed the complexity for a certain amplitude and then having an input or not. But you can use both of these complexities indeed to sort of scan the space of, yeah.
Questions, Natalia?
Yes.
Oh, thank you. I just wonder, can you write it down as a Boolean, in Boolean variables equations, the dynamical equations that take you from the input through the sequence of step to the output?
Yeah, but they're sort of not Boolean functions in the sense that they're direct input-output, right? But you also have memory. But then the system is not fully described as Boolean, but if you do the full description with all the different input levels, it becomes quickly so complicated that it's hard to deal with. So we said, let's just discretize the input, right? I have no input and a certain input, and then you can make it Boolean. Yeah.
But then what particular problem would you intend to solve with the system?
I have no idea. So what we're looking at the moment is really trying to see what is in some sense the expressivity of these materials. And now that we start to have an idea what is there, then indeed we can start to think about sort of designing things and trying to see what you can do. This is not not in the foreseeable future for high-performance computing in a data center, but you could imagine that for embedded computing and little robots and things like that, that's where we typically would like to apply it. Yeah.
Okay, any more questions? Yeah.
So it seems that this system can have more than two
okay, consists more of two states compared to transistor. So how many?
It depends a little bit. So in these sort of cases, the way to think about it is that you have sort of two branches of solutions. So then you really can label these branches 0 and 1. But the fact that you have these branches means that if you couple these elements now, that they have sort of an interaction that is really set by the properties of these branches. In some sense, not different from a memristor. And this allows you to control the coupling and do more with it. You know, if you have strictly zeros and ones, you know, if you want to couple them, then you need logic and you need other things. Here you in some sense use the physics. In this case, it's a little bit less clear if you should think of a 0 and 1. So this one is a little bit more complicated. We can talk about it more, but yeah.
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 Thank you. So we close the first session here and we have a break until 10:55. See you back at 10:55. Thank you.